So for those listening online, both now and in the future, I'm David. In fact, just a second. Hello, I'm David. I'm coordinator of the Maths Learning Centre. And I'll do a revision seminar for Advanced Math Echo 3, and I do have one goal, which I think is probably maybe a bit ambitious, but what my goal is this. Look, it seems like pretty much every tute question begins with the word prove, right, across the entire course. So it's clearly something very important to the lecturer, and it seems like it's an activity you're going to have to do in the exam, is to prove stuff. So anything that I will talk about, any example that I will give, I'm going to try and make useful comments about proving stuff, because that's, it's not technically the Maths Learning Centre's job to teach any content in any course either, but helping you to figure out how to cope with having to prove stuff is what the Maths Learning Centre's job is. So that's what I'll talk about. Yeah. So, well, let me just ask, from the floor, what topics within the course, well, even are there? For a start. Oh, I've got the whole list. Even better. Does it have a list?
Just flick through it. Sorry. There's that ignoring this. There's that lecture notes.
Yep.
Logic.
Yep. Cool. So we've got logic.
Just pull it out if you want.
So is he only going to have in the exam things after the... Okay.
Relations. Functions.
Okay.
Real numbers. Cardinality.
Okay.
And the other stuff I sent you, but this is before the test.
This is like the proof. This is what the term, which is kind of the most important.
Okay, cool. I'll do that then.
And convexity is apparently important.
Cool. So I have now had about 5 people across the last several days say convexity and metric spaces is the go, what we're really most worried about. So sounds like a plan. It is also convenient that I happen to have the lecture notes for those ones. Okay. So the first piece of advice I would like to give generally is that when you're looking at stuff from a mathematician's perspective, like from the maths side of things, as opposed to what it's being used for, which is what this course seems to be about, it's more advanced economical mathematics as opposed to the other way around, is that the definition is the important thing. So to a mathematician, the definition is what a thing is. And so you need to know what the definitions are. So just some general advice. You have to know the definitions, which means 2 things. You have to know how they're said, the actual text of the definitions, and you also have to have some thing about what it means to you. Okay, so what does it mean? Not just to a mathematician, the definition is what it means. There is nothing else. But you want something that, what does it mean to you? So something like a picture, some sort of hand-wavy thing that allows you to have a feel for what the definition is. And then you also need, how does it come up? Okay? So, where do you see it? What things are, what things aren't? What does it look like? Okay? So the details of what it looks like when you're part of the definition and what it looks like when you're not. So examples of things that are or are not, whatever the definition is. And then finally, you actually need to go searching for places in any worked example that you've got, tute solutions or anything you've tried, go searching for places where you used the definition to do something, because that's really useful. That's my way of studying maths. And, you know, an excellent representative sample of one, I got 100% for topology and analysis, which is what this course basically is. So by doing this. So it can't be an awful approach, but it might not work for everyone, of course. So your results may vary. That's just some general advice for knowing definitions. And you also have to know your theorems. And to know a theorem, sometimes you have to know the proof, but you need to know the actual text of the theorem. You know, it says if blah blah blah, then. You need to know what sort of objects is the theorem about. When does it apply and not apply? And hopefully, you know, what can you use it to do? Okay? So, that's our list of things that we'd like to know about theorems and definitions. You might not have answers to all of them, but it's good to ask the questions. And I would recommend, if you're going to have notes for this course, like your exam's what, next week? Yeah, so we've got some time. If you're going to have notes for this course, don't keep these notes. They've got a lot of stuff in them that is sort of extraneous to the definitions. Just pull out the definitions and theorems and just look at just those as a start, so that they're all in one place rather than having to scan through the notes to find them, or at the very least highlight them in different colours. I used to have definitions in blue and theorems in red, just so that I could find them when I was looking for things, because that's what it's all about. And in fact, when you're doing proving stuff, the definition is the key. You must use the definition to do a proof. So and often writing down the definition is the beginning of doing the proof. Okay. The final piece of advice that I would give is find a good way of picturing what's going on. So, now that's picture it in your head or on paper. You don't normally include the picture in your actual exam when you write it, but it's good to have a picture that tries to include the main features of the definition, so that you've got another way of thinking about it, because this maths is all very textual, you know, there's not many pictures to go with it, and most people, even if they learn via text, learn better if there's more ways to imagine things. So having a good picture. And I'll try and do that for the metric spaces and things. Okay. So that's my general advice. Now I'll just talk about the other stuff. Okay. So, just going to have a quick look through. Now look at that. How helpful is he putting each concept on its own page? I didn't notice that when I was scrolling, but when I was flicking through the pages, it became really obvious. So there's a heading at the top of every page. That's kind of cool. Actually, he's more helpful than I thought. Sorry. Better not get him to send out the announcement of where the video is. Anyway, that's why I don't make these public on YouTube, but I often say anyway. So there's a definition of metric space, and then there's all these other things that you can say about them that are definitions in their own right. So let's see if we can collect together the definitions and find pictures of them so that they're easier to understand. And then we'll maybe do some proofs and try and deal with those. Does that sound like a good plan? So a definition, okay, is... Okay, so X is a non-empty set. Okay, so the things in the definition, I should actually go back to definitions as well and say, you know, what things does it apply to? X is a set. D, which sends X cross X to the real numbers, is a function.
Is that a bijection, that X cross X thing?
No. Okay, so that X cross X is not a bijection. It's just saying that the function D acts upon two things in X simultaneously. So it's X cross X, this thing here, means the set of things that are like X1, X2. That's what X cross X means. It's the set of coordinate pairs of things from X. Okay? So basically, that is D acts on two things from X to produce a number in R. Okay, that's what it means. Okay, then D is a metric. That's if, so X with D is a metric space when, let's see, the metric is, so whenever you enact the metric upon 2 points, we call them points by the way as opposed to elements, upon 2 points it's greater than or equal to 0, dx y equals 0 only, no, just a second, if and only if, so I double F is the shortening for if and only if, and as if you've never seen it before, I'm not sure if you have, so if and only if x equals y, okay, dxy is equal to dyx, and dxy is less than or equal to dxz plus dzy. And all of these apply for all x, y, and z in X. Okay, so that's the definition of metric space. Okay, so to understand a definition, that's the actual text of the definition. D is called a metric, and the X combined with D, X with D existing is called a metric space. It's called D because it's short for distance. And the picture that we have in our head is the picture of just the distance between things. Okay, so we know what distance means. We can talk about the distance between here and here, and between here and here. We know what that means. And we're just, instead of having the distance being the number that we thought it was, we can come up with some other crazy definition of what distance is. So that's what a metric space is. So in terms of a picture, all of these things in the definition can have a picture to go with them. Okay? So it's saying that no matter, we've got, that's my set X, no matter which 2 points in the set I pick, the distance between them is positive. So dxy is the distance between x and y. Okay? Except that it might not be actual distance, there might be some other definition of what distance means. Okay? And we also know that the distance from x to y is the same as the distance from y to x. That's what this part here says. Doesn't matter which way you do it, it gives you the same answer. Okay, so the distance from x to y is the same as the distance from y to x. It doesn't matter which way, gets the same answer. So that means that you personally can probably completely ignore what position they go in. Okay, you can do xy or yx, it means the same thing, and it doesn't matter which way around you do it, so there's no point even worrying about it. In the same way that 3 times 4 is the same as 4 times 3, so it doesn't matter, you can write them in whatever order you want. And finally, there's this last one, which is, and the distance between things can only be 0 if they're the same object, okay? So if the distance between them is 0, then they are the same object. That's the only way of, that makes logical sense. And then the other picture is that if you have a point x and a point y and you've got a distance between them there, and you find a third point z, then this distance here, which is the distance from x to y, is shorter than or possibly equal to this distance here, the total green part. So the direct distance between 2 points is shorter than any other distance you could possibly go to get between here and here. The reason it can be equal to, like in ordinary space, if z was between x and y, then it would be equal, because the distance from x to y would be the same as the distance from x to z and then from z to y if z was exactly between them. So that's why it's okay for it to be equal. We draw it as a triangle because it's easier to imagine, but it is actually possible to have the z in the middle and then they come out to be equal. So when you do draw a picture, it's useful to think of the situations in which it could be different to that. I really should have brought something with me. Just give me a second, I'll think about it. I'm going to look in this box of random crap. Nope. Oh. That's from like 2 years ago. No, okay. I was going to give you a nice little demonstration, but I need something stretchy, so it's not going to work. So if I had z in all sorts of different other positions, no matter where z was, even if it was here, it would be all of those distances, no matter where z is, have to be greater than or equal to the direct distance between them. I was going to get a little piece of string and stretch it out and show you that it's longer somewhere else. Anyway. Okay, that's the picture in our head. This is the triangle inequality, which is what this says. And this is that the distance has to be positive. Awesome. And it behaves the same as the way distance does in ordinary places, which is why every time we're going to draw a picture of it, it's going to look like it's just ordinary distance. But the point is that even though ordinary distance satisfies all of these things, other things satisfy it too. And some of them in an extremely basic and trivial way. So here are some examples of things that are. I'm just going to run through some of his. Ordinary distance is a metric on anything that they could have ordinary distance between. A really nice one I have in my head is the distance around the Earth's surface between things. That's not ordinary distance. Okay, so distance. So if you're here on the Earth, right, and you're here in Australia, in Adelaide, and you wanted to get to somewhere else on the Earth, say, Italy, then, I missed India, sorry. Right. Then you could define the distance as following a great circle. So you could follow the distance between them is the shortest distance from here to here. There are any number of distances there, but the shortest one is the distance. And that can be a metric too. But it is an ordinary distance because, of course, the ordinary distance from Adelaide to say, Rome is through the middle of the Earth. Okay? And that's a metric as well. Okay? So it's nice to be able to have a picture that's still geometry, but you can believe that that would behave slightly differently to ordinary distances. Okay. One of the other ones is, he's called it dt, where x and y have coordinates. Okay, so note that x is x1, xn, and y is y1. It makes me uncomfortable that he doesn't use bold to represent vectors, but I'll leave it. I know that mathematicians often don't in this situation. This is called the Taxicab Metric, and it's called the Taxicab Metric for a really good reason. Did your lecturer tell you why?
Yeah.
Oh, good. Because it's to do with a city grid. There's buildings here, so you can't drive your taxi through them, and if you wanted to get from here to here, you would have to go like that or like that. And so the distance is how many steps to the east and how many steps to the north. So you just find how far apart they are in the x direction, which is what this would be, and how far apart they are in the y direction, which is what this would be, and that's your taxicab metric. And it works perfectly well, mainly because it is actually a proper distance. Okay, it's just measured in a certain way. So all of them work great. And then there's the one where you go like, damn, equals 0 if x equals y and 1 if x isn't y. It's a great one. Is that what he called it? Plus? Oh no, that's not plus. Sorry.
Discrete metric.
He called it. He didn't give it a name.
He just called it the discrete metric.
So you just declare that any 2 points are 1 apart. That's it. Great. It's an awesome metric. This is in fact what they use in coding on the internet, because of course if two sets of text are different, well, yeah. So there's one where you just count how many coordinates are different. That's another one as well, which he didn't give you but there's one where you count how many of the coordinates are different, and then that's the metric. So they're all great metrics. And then there's the French railroad metric, which is saying that it took me a while to understand it from the lecture notes, but there's a particular point here, which is apparently Paris, and the distance between any point and any other point is this distance here. And so that's how far it is from x to y, because you have to go through Paris. Yeah, so it's like the distance between x. The French distance between x and y is where that's a magic point x star that you use for every other point.
What metric is used to find like the distance between x and Paris?
Some other metric. Yeah, I believe he said that this is supposed to be, ordinary distance. Yeah, sorry, Euclidean, that's the correct name for it. But technically you could imagine that from any metric you could create the French railroad version of the metric by doing this process. And that would be an awesome exam question. If I was writing the exam, I would say, given any metric D, show that the French metric is still a metric. I think that would be a great exam question. In fact, maybe I'll choose it as my example. Remind me if I don't. Okay, so they're all great, and even better to get a feel for them, though we don't really have time, but you might get a feel for them, is to actually draw some points and figure out what the actual distances between them are, and look at how the distance is always positive and how the triangle inequality actually works. So if you're going to do the taxicab metric, you can do it. So I just have a recommendation. If I go back to the taxicab metric, did I do that last? Not quite. back to the taxicab, actually draw yourself a grid and figure out how far everything is from everything else. You know? So this would be 0, 1, 2, 3, 4, 1, 2, 3, and we can go the distance between the point 0, 0 and the point 1, 3 is 1, 2, 3, 4, which is that distance plus that distance, you know, and the distance between 1, 1 and 4, 3 is 1, 2, 3, 6. But that works because it's from 1 to 4 is 3, and from 1 to, so from, that's not 6, is it? 1, 2, 3, 4. Did I have 1? Oh, 1 is there. 1, 2, 3, 4, 5. Sorry, 5. From there to there is 3. From there to there is 2, and 3 plus 2 is 5. You can get a feel for how that works. The reason I do that is because that means that you now have 2 ways to try and understand a thing that you're supposed to prove about metrics. If you can draw a taxicab metric picture and an ordinary distance picture, you might be able to understand what it is about the metric, about the definition of metric that makes the theorem work. Okay. All right. That's the definition. It appears, according to the first theorem in your notes, the first question in your notes, that actually you don't need all of the definition to actually prove that it's a metric. You only need to show that it's equal to 0 when they're equal. You know, it's only 0 when they're equal, and the triangle inequality works. And that's enough to make the other things true as well. So if you are going to prove that things are metrics, I have a feeling that you're allowed to just do that, but I could be wrong.
So we don't have to prove that like dxy is the same as dyx?
Apparently this does it. But
So it's an answer.
that would worry me. So to prove that based on this it's a metric, you would have to prove that the other things would be true, like to do this question. But technically the upshot of that question means that if you wanted to show that something's a metric, you don't actually have to check the other rules because it follows anyway. Yeah, and I have a feeling I can think about how that would actually work out. But I don't know if your lecturer will feel comfortable with that, so it's probably safest to just do all of them. Because usually the dxy equals dyx is fairly obvious. Because you just sub it in the other way and go, oh look, it comes to the same answer. So, yeah, okay. All right. I'm just going to see if I can run through and talk about all the other things he said about all the definitions. So that was the definition of metric space, and we had some examples of things that are and things that aren't. The next definition that we find is actually a question, and it's a ball. So we have another definition. That's my shortening for the word definition. Sometimes I just write def. So we have another definition. An open ball of radius r is denoted by center x is denoted by bxr, the ball centered x, radius r, and it's an open ball, is the set of x's in x such that the distance, no, sorry, not x's, y's, such that the distance between x and y is strictly less than r. That's the set notation definition of it. And remember that it's important to realise that when you define something with set notation, it's giving you a rule for telling whether an object is in the set or not. So if I have a random point y, I can tell if it's in the ball by checking to see how far from x it is. That's what this says. If you check to see how far from x it is and that answer comes out to be less than the radius, then you're in the open ball. Okay? So that's the definition. So the picture that goes with that Oh, just a second. The closed ball, which does that have it doesn't have a notation, but the ball would be closed if it wasn't or equal to. I would say that it would be that.
Yeah, that's what he uses it later on, like another close it something like.
All right, cool. That would be the most natural thing to use, so I'm glad that he used it. Okay, so in terms of pictures, you've got a point X, which is the center, and you've got the way to tell if a point is in the ball is if it's closer than a certain distance. So that's my distance R, and my open ball is all of that. But the open ball doesn't have the edge. And the closed ball does. We should see what it looks like in Taxicab Metric. So this is Euclidean. If you have a point here and you have the ball of radius 2, well, that point there is 2 away. And that point there is 2 away, and that point there is 2 away. One, two, 1, 2, 1. So all the points within that is the open ball of radius 2. So my open ball of radius 2 contains, it doesn't contain the ones I've done in open circles. That's my open ball. So green is the open ball, that's X, around X of radius 2. Whereas these ones and these ones, that's the closed ball.
Wouldn't you also have a point closer than those closed dots on the edge of the circle?
I believe the taxi... Yeah, you could. It depends. In my head, the Taxicab metric doesn't only applies on the grid points, but you can have it on the others too, and that's fine.
So
Yes.
that would be like discrete.
Sorry?
Like you just have grid points be like discrete.
Yes. So
You say the elements of N or something.
yeah. So you can define. In my head, the X when I'm doing Taxicab metric is just only has whole number coordinates, but you can do it with any coordinates at all as well. So, yes. I'll do it like that. Hey? The coloured in bit is the open ball of radius 2. So if you're allowed to use any points, because in my head the reason it's a Taxicab metric is because there's buildings in the way and you can't even be in those spots, but yeah. So balls in the Taxicab metric are actually squares, which is interesting. And some crazier metrics, balls are, yeah. In the discrete metric, balls, well, there is only, balls are just single points. That's just the way they work. Okay, cool. Right, that's an open ball. Awesome. So, key point about anything that is a definition of a set is that this bit here is the rule for telling if you're in a set or not. Which means when you do a proof, that will be a key part of the proof, deciding if that is true or not. Okay, so I said it's open if for any x in the set there is an R such that there is an open ball around it that is in the set. Right. So this is the thing. A set S is open when, for all x's that are in S, there is an R greater than 0 such that the ball around X, the open ball around X of radius R, is contained in or possibly even equal to S. Does it have to be centered on X? Yes, okay. I have heard it defined in other courses as just there is an open ball centered somewhere that contains X, but which makes it so much easier because then an open ball is automatically open because every set in it is in an open ball. But they don't do it in this one, so it has to be the open ball. So basically the picture is your set, just a random set, is open if no matter which point you pick, it's possible to pick and find an open ball that's completely contained inside the set. And if you're really, really close to the edge, you might have to choose a really, really small R. But as long as there is an R that's small enough, you can do it. This set is, so if this set doesn't include its boundary, then it will be open, okay? But the problem happens if this boundary is part of the set. So I'm just going to turn this into a dotted line. Okay? No matter how close you get to this edge, you can always make the R even smaller and fit a ball inside the set. A set won't be open, so this is just my picture. A set won't be open, so this is open. A set won't be open if there are points, so no matter which ball you pick on that point, it can never be inside the set. So if I have some set that I've got some set like this, and I'm just going to get a magnifying glass and zoom in here, right, on the edge. There's my point X there. So here we are inside, zoomed in, and there's the edge of my set, and there's X, right on the edge. No matter which open ball I pick, it can never be contained inside the set if it's centered on X. So I could pick that ball, but it's got some bits that are outside the set. I could pick that ball, it's got some bits that are outside the set. I could pick that ball, it's got some bits that are outside the set. No matter how close we go in, no matter which ball we pick that's centered on X, it can never be completely contained inside the set. It'll always have some things that are outside the set. That's what not open.
What about that, the ball you just mentioned before, not the Euclidean, not the Taxicab, but that other distance ball?
The discrete metric?
The discrete metric, that's just a dot.
In a discrete metric, all sets are open.
Oh, okay, right.
But it's a worthwhile thing to note. Let's do the discrete metric. So in the discrete metric, so in the discrete metric, if you have a point X, every other point is exactly 1 away, right? So every other point, the distance from here to there is 1, because that's how the discrete metric works. Okay? This distance is 1, this distance is 1, this distance is 1, this distance is 1. Okay. So if I have the open ball centered on X of radius, say, 1/2, there are no points that are half away. The only point that satisfies the definition of this, so this is the set of points Y in my set such that the distance between x and y is less than a half, right? Well, there's only one point that's less than a half from x, and it's x, because it's 0 from x. So that's just the point x. So every open ball of radius less and that therefore every point all by itself is an open set. Yeah.
Right.
Is that R to be equal to 2, or can you not have the radius greater than the greatest possible distance?
No, you could do that. The ball x2 would be the set of y's in x such that the distance between x and y is less than 2, which would be everything. Because everything's 1 away. Okay, so your open balls are either single points or the entire of x, which is really quite bizarre. Yes. So basically, in the discrete metric, everything is open. Okay, so we're doing well. We're getting a good understanding of how this works, but this method of understanding things works. Because we're going, well, what would happen in this metric? What would happen in this metric? How would that look? How would this look? You can get a feeling for how things work. And it's a bit, if your measure of distance behaves and it can only have certain numbers, then balls are going to just suddenly jump when they get to a certain spot. So this can only have the number 1 and 0. Everything less than 1 is here. Everything more than 1 is everything. But suppose you had a discrete metric that had 0, 1, and 2. Then there'd be 3 sizes of ball. Okay. All right. Now we have the definition of closed. A set is closed when its complement is open. Which is great. So it is possible for a set to be neither open nor closed. You can imagine something that has half of its boundary filled in, the other half dotted. It's neither open nor closed. It's possible for a set to be both open and closed. That usually only applies to the really big or really small set. So in the discrete metric, everything's closed too. So everything's open, everything's closed. And that's true in the Taxicab metric too. Only if using discrete points. But anyway, so the set is closed when its complement is open. So what does that look like? Well, that means that it's possible. So if this is a closed set, then when it's closed, that means the complement has to be open, which means if you pick a point outside the set, it's possible to put balls so that they're completely outside the set. Okay, that's the idea. So a set is open when open balls can be made to be inside the set, and a set is closed when open balls can be made to be outside the set. Yep.
In an example, could we simply just say set is closed? Like if you prove that its complement is open, we'll just say that it's closed.
Yep. So yeah, in an exam you don't have to do this thing unless you've gone to all the effort. You have to prove it. If you happen to know by some other reasoning that the complement is open, then you can just say it's closed because that's the definition. Okay. Right. So the empty set is both closed and open. Yep. The whole space is both closed and opened, and the empty set is both closed and open. And that's true in all metric spaces. And that's because if you've got the empty set, well, there aren't any points to pick. So if I could pick one, I could say whatever I wanted about it because there aren't any. So yay. And its complement is everything, and all the open balls are contained in that. So it's open, and therefore the empty set is closed. So writing that down as a proof was fun in the Maths Learning Centre a couple of weeks ago. So. Okay. So why do we care about closedness and openness? Not entirely sure at this stage. But there's one more definition here. Definition a set S is bounded if it is contained in an open ball. Which makes sense, right? The concept is that there must be a centre that you can pick such that everything is within a certain radius. And if there isn't, if no matter which point you pick, and no matter which radius you pick, there's another point that's outside, then my set goes on forever. It's not bounded. Okay? So imagine this straight line here as my set S. I could pick a ball here, but it wouldn't cover all of it. I could pick a ball here, it wouldn't cover all of it. I could pick a ball here, it wouldn't cover all of it. No matter which ball I picked, it would never cover the whole of the set, so it's not bounded. Okay? I can't pick a ball anywhere that will cover the whole set, so it's not bounded. That's the definition of bounded and not bounded. So basically that means if it's bounded, then if you look at the distances between every point and every other point inside the set, they have to have they can't go past a certain size. Okay? So basically, distance in a bounded set can't be bigger than some upper limit, right? But this set here, if I pick 2 points in them, I can pick them to be as far apart as I want, and I can get as far apart as I want, and therefore there's no limit to how far apart they can be, so it's not bounded. Of course, if I was using the discrete metric, there is a limit. Maximum is 1. Everything's bounded. So, yeah. Taxicab metric, there are unbounded sets, because you can make the metric as big as you want. Of course, in general, an unbounded set has to have infinitely many points in it. In fact, it must have infinitely many points in it. If it's only got finitely many points, you can just calculate all the distances and pick the maximum. Ta-da, bounded. That's the maximum distance. Okay? So, if it has a maximum distance, it doesn't have to be finite. But if it's finite, it would have to have a maximum distance, so it would have to be bounded. And that would be a really nice part A to a proof question. You know, prove that a finite set must be bounded. So, yeah, you could argue that way. And then the final definition, got all these terminologies. This one's more of a terminology than anything else. A neighbourhood around X, of X, sorry. Of X is any set containing X that contains an open set. And that seems really general, right? So, well, containing X. I don't know why he doesn't just say a neighbourhood is an open set that contains X, but, you know, whatever. So the point is that here is X. Here is an open set around X. That there would be a neighbourhood because it contains an open set that's around X. Basically, a neighbourhood is just something that's sort of close enough to X. And it's just, we define it so that we can start we can be a bit less specific when we talk about things. We can just say, well, if there's a neighbourhood, and then we can let the reader figure out all the details for themselves.
So would an open ball of centre X radius RB and a neighbourhood of X?
So classic example is an open ball around X. So an open ball around centred at X is a neighbourhood of X. So technically, any open ball that contains X, even if it's not the centre, is a decent neighbourhood. And in fact, when I did this course, my lecturer, not this course, but the maths version, my lecturer defined a neighbourhood as an open ball that contains your set, that contains your point. So that's probably worthwhile just thinking that that's what a neighbourhood is, but this is the definition just in case he asks. I'm pretty sure he won't. But yeah, the upshot is that if X has a neighbourhood somewhere, then X has an open ball around it. So really, it might as well be open ball. Okay. Now, what does all that mean? So far we've got this concept. So we started with a distance. We started with a distance, some way of measuring distance between points. And then from that distance, we've now started to be able to say, we can make balls, circles. We can make balls. And then from balls, we can make open sets. So we've gotten very quickly to being able to classify any set whatsoever as open or not open by just using distance. So all of this came originally from just the definition of what distance was. Changing a definition of distance will change what it means to be a ball, what it looks like to be a ball, but the rule is still the same. It's based on being within a certain distance. Okay. Right, let me just see if I can... Okay. But there is something else we can do with distance. If you can tell how far apart points are, then that means that you can tell how close they are, which means that you can start doing paths. You can think of a path that goes from one point to another and moves around, okay? And what we want to do is, well, does that path go somewhere? So that's the next thing in my head. So the next definition is sequences. The definition of a sequence is a function f which sends the natural numbers to x. Okay? But even in your notes, you don't use it that way. You just list. So that basically means there's a list, like 1, 2, 3, 4, 5, blah, blah, blah. And then there's an x1, an x2, an x3, an x4, an x5, blah, blah, blah. F takes 1 to here, 2 to here, 3 to here. A function from the natural numbers to x is really just a list of x's. Okay? Like that. And you usually denote it by xn. Okay? I think of a sequence as a path, a journey that says starts here, goes here, goes here, goes here. So I can imagine here's x1, then there's x2, then there's x3, then there's x4, and I keep going. Okay? That's my picture in my head, because remember they're metric spaces, so everything should be able to be talked about how far apart they are. But the sequence has to go on forever. You have to go round and round forever. Okay? It may be that some of the steps go to the same point, and this is also x7 as well. You don't have to actually go to a new point. Okay, so the sequence can be anything. But some sequences will do something kind of cool. They will converge. Right, they'll get closer and closer to some final point. So you can imagine it spiraling around or going in and out and eventually just getting closer and closer and closer. That's converging. Okay, and you can do it with just plain numbers as well. You can imagine a sequence of numbers on the number line. Here's x1, then there's x2, and then there's x3, and there's x4, and so on, and just jumping round. It works very well if you think of it as a picture of where the numbers are rather than just a list. It is a list, but thinking of it as a picture helps to understand what a Cauchy sequence is. So, here are some more definitions. Sequence converges a sequence xn converges to x when for any epsilon there is an n which is an integer such that the distance between xn and x is less than epsilon for all n greater than or equal to n. That's the definition. He's also got a neighbourhood definition. Converges to x. For every neighbourhood of x, there is an integer such that, so this is the or, xn, or when, for any neighbourhood of x, which we shall call v, there is an n such that xn is in v for all n greater than or equal to n. So let's think about what that means in terms of the picture. That's my metric space. In fact, this is, So imagine you've got your points, your path, and this is my point x here. Sorry, ask because my writing can get worse as the time goes on. What does what say?
Just before, on the last line, just before it says for all n greater than or equal to n. Oh, just on the very last line, sorry.
Down here?
Yeah, just to the left.
Oh, xn is in v. Sorry, the document camera is a bit dodgy too, and then compounded with my bad writing, it's not doing well. So you're doing a sequence, it's moving around. That's my goal point x, that's the thing that it converges to. And that's saying that no matter what distance I want to be around x, I could choose this distance, that's an epsilon. Then there is an n. If I go far enough in my sequence, everything beyond that point is inside this ball. That's what that's saying. So up here I've got n equals 1, n equals 2, n equals 3. After 4, everything's inside this ball. So that's my capital N would be 4. But for a smaller epsilon, it might take me up to 6 or 7 to get that far. For a smaller epsilon, it might take me up to 100 to be able to guarantee that I'm always inside the ball past that point. Okay? And neighbourhoods, you're just not specifying the shape of the set, you're just random set. Okay? So remember, being inside a certain distance is the same as being in a neighbourhood. Right? It's the same as being in a ball. Being within R of x is the same as being in the ball. And so that's my epsilon. So this statement here, look at it. The distance between xn and x is less than epsilon. That's the rule for being in the open ball around x of radius epsilon. It works on a number line too. The classic example is to start with 1 and then choose as your points 1, a half, a quarter, an eighth, a 16th, like that. So no matter, and the goal is 0. So no matter how close you want to be, if I go far enough, it'll always be inside there. And this close, I'll just have to go a bit further. Okay, that's the idea behind it. So just as part of this definition, x is called the limit of the sequence. Right, doing well. So again, this is just something that we might want to do. We imagined as things having distances between them, but then we're going to have a sequence of this one after the other, and we're looking at the distances between them and where they're headed to. A Cauchy sequence I was saying it with the correct pronunciation, it would be Cauchy, because he's French. Cauchy. It's really funny because if you look up Cauchy sequencing on Wikipedia, it tells you how to pronounce it in French and in English. It's like, okay, sure. It's not that different. It's using the nice international phonetic alphabet. A sequence is Cauchy when... Now, where's his definition? Yep. For any epsilon, there is an n so that the distance between x m and x little n is less than epsilon for all m and n greater than or equal to n. Okay, it's very similar to the definition of convergent, but there are two really important differences. One is that we have two, an m and an n, little m and a little n, as opposed to just one little n. The other is that we don't know what the limit is. The definition of Cauchy doesn't include this magical x that it converges to. Okay? What it means in terms of the picture is that no matter what size ball I'm interested in, there is a point where everything after a certain, all the points in the whole sequence after that capital N fit inside a ball of that size. Okay, it doesn't have to be centered on anything in particular. So that's saying, well, suppose I want my distance to be this distance here, that's my epsilon. Then I'll go here and go, cool, I can fit, it'd be epsilon on 2 technically, everything after this point is within that distance of each other. That's what this says, all the points after that. And then the next thing is if I choose my epsilon to be even smaller, then cool, everything after this point is within that size. So the ball moves because it's not necessarily centered on the limit. Okay, and if I zoom in even further and I wanted a really tiny epsilon, if I just followed the path long enough, every part of the path beyond that is within a little zone. Okay, they're all closer to each other than that. Yeah. You would expect that Cauchy sequences would converge, but they don't have to. Okay, and there's this final definition which he did not give you in your notes, but it's worth pointing out now because he used it in the definition of the contraction mapping theorem. A metric space XD is complete if every Cauchy sequence converges to a limit x which is actually inside x. So the key point is that if you just take the numbers between 0 and 1, not including 0, not including 1, there are plenty of Cauchy sequences, but their limit is 0, for example, and so it's not inside the set. So Cauchy sequences, I believe, for most metrics have to converge to something, but it might be that your set isn't big enough, that there are missing points in your set that don't converge. So you can actually create a new metric space by adding in all the things that the Cauchy sequences converge to, and that's called the completion. So the real numbers is the completion of the rational numbers. So if you take fractions, you can create any real number from a sequence of fractions by just using its decimal expansion. You go 4 decimal places, 5 decimal places, 6 decimal places. They're all representable as fractions. And so the number pi, even though it's not a fraction, can be a sequence, is the limit of a sequence of fractions. And so, yeah, the rational numbers are not Cauchy under the ordinary distance, but they are not complete, but the real numbers are. Cool bananas. Okay. Oh, but if it does converge, it has to be Cauchy, which makes sense because they all had to be close to this, so they must be close to each other. Right. So there is an alternative definition of closedness then, if you want. So far, our definition of closed was that its complement was open. Now we have a new definition of closed, which is also true. A new definition for closed. A set X is closed when a sequence, any sequence all of whose elements are in S, okay, any sequence of things that are in S which converges to a limit has the limit inside S. So it's saying that if you happen to find a sequence which does converge, so a set is closed if no matter which sequence you happen to pick which happens to converge, then the limit is inside S. So open sets are not, well, they can be if they're both closed, but most an open ball is in general not closed because you can do your sequence which will converge, and maybe we'll go back and forth here, and it might converge to something that's on the boundary, but the boundary is not in the set. So you can get as close as you like to that convergent point, but because that point's on the very edge, you can get as close as you want without leaving the set, but the moment you get to the limit, you've left the set. So, not closed as sequence converges to X, which is not in S.
If we got given a question, we have to prove that a set was closed, because we just show that it's open and therefore the complement of the open is closed and just use that.
Yeah, so you don't have to use this definition to show that something's closed. So you are allowed to use the old definition. But if it happens to occur to you, so if the rest of the question was about sequences, it may be easier to go, oh, this random sequence converges and its limit isn't inside the set. Cool, not closed. So this is probably a much quicker way to show that something's not closed than to show that something is closed. The quickest way to show that something is closed is to show that its complement's open. But this is basically telling us a fast way to show that something is not closed, which is not the same as being open, sadly. Damn mathematicians and their use of words. Okay. And then finally the definition is the closure. Given a set S, closure, which is called S bar, is the intersection of all the closed sets that contain A. Containing S. You can also think of it as S including all of the limits of all of the sequences that are in S. That's the other way of thinking about it. So the closure of an open ball is a closed ball, which makes sense, hopefully. Okay, so if you've got something defined with dotted lines, you know that set there, its closure will, all the dotted lines will become hard lines, basically. Cool bananas. Success. All right.
Sorry.
What's that?
How is that the case?
So instead of, there is a different definition which says that you add to S all the limits of all the sequences that are in S, right? So there's a sequence in S which jumps to the edge. Yeah. So S doesn't have to be open, it could be any set at all. And if it, basically if it's got this dotted line at the edge, the closure will include the edge. You just add the edge to it, basically. So the idea is that I could draw a closed set that contains this, I could draw any number of closed sets that contain this. And the only part that will be in all of them will be this. And the reason that's true is because every closed set contains a limit of all of its sequences. So I can think of making a sequence of jumps towards this edge and getting closer and closer to a point on the edge. So since every sequence's limit has to be in the closure, that point on the edge is in the closure. And this sequence, its limit, which is on the edge, is in the closure, that point's in the closure. So you can think about it in terms of going sequences that go to the edge, and you include all of those edge points. But these points were already cool, they were fine anyway, so they're still in the set. Yep?
Would a closure of like a closed donut include the center ring?
No.
Okay.
So the question is, the closure of this is the same as it was before.
What if they were open?
It would still be this.
Okay.
Yeah.
So it doesn't include the actual center.
No. And that's because, if we think about it, in terms of sequences that live inside this set can't reach that center. If I draw a path, I can't get into there, so none of the limits of any of the sequences that live inside S can be there, so I can't add them to it to get the closure. That's why closure, I think, is here at this spot, because it's easier to think about closure in terms of sequences than it is in terms of open sets. But the definition is that it's the intersection of all the closed sets. But remember that all the closed sets contain the limits of the sequences, so any limit of any sequence that's in S has to be in the closure, because all closed sets contain their limits. All right. This has taken longer than I thought, but is it useful?
Yeah.
Okay, right. I may, I'll think about that later, because I'm probably not going to get to the other thing, but I will get to the contraction mapping theorem, because that's in metrics. So I'm going to finish metrics. Okay. So, right, let's just see where we've been. We've used our distance to define balls, and from balls we've defined openness. Then we've taken a different tack and we've done little paths of dots that follow around each other, and sometimes they approach limits. And we've used balls to help us to define what it means to approach a limit. And then we've used limits to help us think about what it means to be closed in a new way. Okay, that's where we are. Awesome. Okay. So, right. So, a continuous function in real analysis is a function that preserves limits of sequences. I don't know if that's how it was defined to you.
He very briefly talks about continuous mapping that very, very, very briefly.
Yeah. So I am talking about that.
Yeah.
Yeah. Sorry, just a second. Can you say that again?
He very briefly talked about it.
Yeah, because we need it to do the contraction mapping theorem, right? So, right. Let's just think about this. You need a new way of thinking about functions in order for us to do this. So, we did functions. we did functions, and they were very esoterically defined as, like, you know, subsets of the Cartesian product, and there were relations and there were functions and whatever. But the easiest way to think about functions pictorially, so this is my pictures, is to think of a before picture and an after picture. Okay? You've got all your points before, and then what they became after when you applied the function to them. So before and after pictures are great. So I can imagine the function f of, this is a real number function, so for x in the real numbers, f of x equals x squared. I can think of that function as a before picture. Maybe I'll just do it on the natural numbers so it's easier to describe. And that's minus 1. No, the z, the integers, z. Minus 2. Okay, that's before. And you are really used to, hopefully, drawing this as a graph, you know, with like a parabola or something. But we could see where all those points go when I apply the function to them. So 0, before it was 0, and after it's still 0. That became this thing here. So I'm just going to color code them. That point ended up here when I did the function. Number 1, when I did my x squared, it ended up here at number 1. But the point minus 1, when I did the function, whoa, green is green, it ended up here. Because when I square minus 1, it ends up being 1. And the point 2, pink, well, it ends up here. Okay, so that's my after. This is going to make sense of the contraction mapping theorem. Okay, so each point before moves to a new location after when I apply the function to it. Okay, so you can do this as well in other places. So that's just an example. So what if I had this time my function of my point x in 3D space is like half of x. Okay, so treating it as a vector and dividing it by 2. So this point here, when I divide it by 2, will still be there. And this point here, when I divide it by 2, it'll end up just here. Change my color. And this point over here, when I divide it by 2, will end up here. And you can imagine that a cloud of points would all be pushed further in. Okay? So this is where I just pick any collection of, it acts on all the points simultaneously, so every point moves to a new point here. But I can imagine if I pick a certain collection and see what happens to it, I can see that this collection gets smaller. They're all closer together. Okay? That way of thinking about functions will make sense, hopefully, of the contraction mapping theorem. So, a continuous function. Right now, we're going to get our definition. Oh, I should point out, it doesn't have to go from the same place to the same other place. Okay? It could go from here to the real numbers as well. So, I just want to do another one, just a second. F of the point with coordinates x, y, you like x plus y. Let me do that one because I just want you to see how it works. This is before. And my after Well, it's just a single number afterwards, so it's just a single number afterwards. So before the point 0, 0, that point there, its coordinates are 0, 0, and so after it will be here at 0. This point may be here, and maybe I'll give that one coordinates, maybe it's 1, 2. After, it'll be here at 3. Okay? This point, I've already used green. Where'd my pink one go? This point, maybe, well, let's try. So what's that? That's about like 1.5, 2.5, 0.5. Will also end up here at 3. Okay? And then all the points here end up somewhere here. You can think about it as this somehow gets squashed onto that. Somehow. And it's possible to think really carefully about how that works and to know precisely what will happen. In fact, there will be a straight line through this, and all the points on that straight line will end up here, and all the points on this straight line will end up somewhere else. But that's a story for another day. Okay, so functions can be thought of as before and after pictures, and that makes sense of everything about continuous functions with metric spaces. Okay? So my definition, function f which sends x to y, so that's my before, that's my after. Okay? And this has they both have their own metrics, possibly not the same metric. Okay? Then f is continuous at a point x naught when for every epsilon greater than 0 there is a delta greater than 0 such that the distance between distance in y between f of x naught and f of x is less than epsilon whenever the distance in x between x naught and x is less than delta. And f is just the word continuous as opposed to continuous at x when it's continuous at every point. Now what does the picture look like for continuity? Well, it goes with this before and after picture thing. So before is where this is x here, and after this is y here. Okay? What we're saying is, so let's just read how the definition goes. It goes, when, no matter what epsilon is, if the distance between, okay, we need the point x naught. So here's the point x naught. And here is the point x that they are referring to. And the point x naught ends up over here maybe. This is f of x naught. Okay, because remember f, when I apply it to this point, produces another point over here. And yeah, that'll do. And maybe this is f of x. So x was here and f of x is here. Okay, that's the idea. And I'm interested in particular in this point x naught, and I can move my x around to various different places, and this f of x will move. So maybe this will go here and the f of x will do something else. So I can imagine what happens to that. And then my idea is that if I pick an epsilon over here and I say I want, that was bad, but anyway, that's my ball about radius epsilon. Okay, it's not symmetric, sorry, but that's okay. This is my ball of radius epsilon. So pick an epsilon, then it's possible to pick a delta here. Delta.
That ball's meant to be centered around F.
Yeah, it totally is. Sorry. If I make my y bigger, that will make more sense. Is that better? Not much, sorry. Anyway, it's centered at epsilon like that, because remember, this distance between here and here is less than epsilon is the same as saying you're in a ball. That's saying that there is a ball, no matter what epsilon is, I can pick a ball, I can draw a ball around f of x naught, and it's possible to come back over here and find a ball around x naught, such that every point in here ends up inside there when I do the function. Okay? So all of these points here, when I apply the function, end up in there. So it may be that this ball ends up, looking like something crazy when I actually do the function on all of the points, but as long as it's inside here, it's okay.
So does that mean every continuous function is going to be a ball, open ball?
Well, no, the function itself takes all of these points and produces some points over here. That's a good question. I believe continuity preserves openness, yes. So if you do the function on the entire of x, then the points you end up together at the end, you might miss some points in y, but everything that you do achieve has to be open, yes. You've thought of another classic exam question. I don't know if it really will be. But if I wanted my epsilon to be smaller, I would need to choose a correspondingly smaller delta so that the whole ball here fits inside there when I do f. Right. Awesome. It doesn't tell you what delta pick, you just know that there has to be one. Often it's like half of epsilon or something. Right. Doing so well. Oh no, I'm trying to pep myself up for continuing, right? No, we are. We're nearly there. We're like on the second last page of So just a second. Right. So there is an alternative definition of continuity. So a new definition. So there's an alternative definition of continuous on the next page, which says f is continuous at x naught if for any just a second, stop, just a second. This is not a definition. Ignore that. I will put it down anyway because it is here. If for any neighbourhood V of x naught of f of x naught, there is a neighbourhood u of x naught with f of the whole neighbourhood is contained in V, which is exactly what I just drew. Okay? So f is continuous at x0 if for any neighbourhood v of x0 of f of x0, there is a neighbourhood u of x0 with f of u is in v, which is what this picture is describing. This is my neighbourhood v, this is my neighbourhood u. It's the same picture. Can I fit them both on the screen at the same time? Yes. So that's my v. No matter which v I pick, it's possible to pick a u around x somehow so that when I do the function on this u, the entire answer is contained in v. But there's this theorem, and it's really important to have a theorem at this point. My theorem goes, f is continuous if and only if for any f, this is continuous on the whole set, right? If and only if for any open set V which is contained in Y, the pre-image of V is open. So that's saying here's Y, here's X, this is my before, this is my after. No matter which open set I pick here, that's my V. If I go back and figure out all of the points that end up here, that's what F inverse V means. If I go back and go, right, this point ends up there, 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 this point ends up there as well, and I go and find all of those points, this is the pre-image of V. Okay, so it ends up in that spot there. This is open as well.
Is that the inverse function?
No, it is. The function might not have an inverse. It's the pre-image. So it looks like the inverse function, but it might not be because the function might not have an inverse.
But it did have an inverse, so the pre-image.
Yeah. So if it did have an inverse, that would be the inverse function enacted upon V. But if your function doesn't have an inverse, it just means find all the points that end up in V when you do F. That's what that's what this means. Okay? So if you pick an open set V, if you go back and find all the points over in X that end up in V when you do F, and you collect them all together, that's the name of this function, F inverse V. If that set, when you find it, is open every time, then it's a continuous function. So continuous functions preserve openness. Right. But you have to define it backwards. It's not good enough. It's not good enough for your function to just take every open set here and produce an open set here. It has to work the other way. It has to be that if you want to produce an open set, you have to start with an open set. So some functions...
Closed set?
Sorry?
Is that true for a closed set?
No idea. Sorry. If you start with it might be possible to start with a closed set and end up with an open set over here, and then it wouldn't be continuous. I think it would also be true for closed sets. Any closed set here should be a closed set there, because I know that continuous functions preserve sequences as well. And since you can define closed using sequences, it should work. Yeah. Right. Okay. And now we have, finally, the contraction mapping theorem. I'm going to draw a picture of this before I write down the statement. Okay, so this is not the mapping theorem that's a contraction. It's the theorem about contraction mappings. Okay? Right. In the same way as French onion soup is onion soup that is French, as opposed to soup made from French onions. So this is the theorem that is about contraction mappings. So a contraction mapping is a function such that everything's closer together after you do the function. If you pick any collection of points and you do the function, then the new points are closer together than they were before. That's a contraction mapping. Okay? And so a contraction mapping theorem is specifically designed for looking at functions that take a set into the same set again. Okay? They go from f to x to x. That's my set x. And it's the same set x again. See, it did pretty well, didn't I? Okay, the point is that this is the same set before and after. I wanted to draw it with an interesting shape so that you could tell. It's sort of roughly shaped like Africa, according to my previous drawing skills. Okay, so the idea is that if you take any collection of points, or just any 2 points, and you look at where they go after you do the function, they'll all be closer together than they were before. Okay? That's a contraction mapping. Things become contracted. So no matter which distance you pick, so these 2 points maybe have this distance, and afterwards they're here and the distance between them is smaller. Okay? Now it's not good enough. The contraction theorem, that's not good enough. It's not good enough to say that every distance is shorter than it was before. So the before points and the after points, the distance is shorter. You have to be able to guarantee that they'll all be like 80% shorter or 20% shorter. They will have to be the same percentage, not the same, but less than the same percentage shorter. Okay? So if you look at the comparison between every distance and every other distance, they all have to be below the same level. Okay? So if you just said they all had to be shorter, it could be that one of them just became a weensy bit shorter and another one became an even tinier weensy bit shorter. You need them all to be the same, at least the same level shorter. Okay?
So that is like they would have to be like a tiny weensy bit shorter, and then it's
Well, as long as... So the idea is that you have to be... you're not allowed to be able to go... If I said to you, pick a tiny weensy bit, and you said, hey, look, these ones are only that much shorter, and no matter which tiny weensy bit I picked, you said these ones are only that much shorter, then it wouldn't work.
So it has to be like a fixed ratio.
It doesn't have to be fixed, it just has to be, there has to be an upper limit. Okay, so if you look at the ratios of all of the distances before and all the distances after, there has to be an upper limit to that ratio that isn't 1. Okay, so if you did a list of this distance divided by that distance, this distance divided by that distance, this distance divided by that distance, you did all those numbers, it's not like, if you take the limit of those numbers, that has to come to like 80%. But it's not allowed to come to 100%. Okay, so it's not like if you do the list of all of them, it's possible to go all the way up to 99.9999 and 99.9999. Yeah, there has to be a point at which you can say, yes, they're all less than this. So you can imagine if there are infinitely many points, setting it up just right so that it was always possible to get closer and closer to 100% by picking the right pair of points. Yep?
Wouldn't that mean, unless they're all fixed, like percentage smaller than, wouldn't that mean that the after set wouldn't look the same as the before set?
Oh, well, no, it's just going here. You're right, you're not going to be able to cover the whole of this afterwards.
Yeah.
Right, so there's going to be ones that no point ends up here, but when you say x goes to x, it's just, these are the options for what it could be. So yeah, when you say f sends x to x, these are all the things that you must be able to use, but these are all the options that it could be, but it doesn't have to cover them all.
Yeah.
But you're right, if I take all of these points, I won't be able to cover all of them because they're all closer together than they were before. Oh yes, okay. My phone's reminding me of something, but that was cancelled, so it's all good. Okay, so now I can... Right. That is what a contraction mapping is. Okay, that's not the definition, but that's what the definition means. So now I can say the theorem because it'll make more sense now. F sends x to x. Okay. X is complete, meaning all of its Cauchy sequences converge. Yep. And there is a k with 0 is less than or equal to k is less than 1. Okay, so it's a percentage. Such that, so this is my setup, you know, if all of these happen at the same time. So it's like if this, this, this. So there is a case such that d of f of x, f of y is less than or equal to k of dxy for all x and y in x. Okay? So that's what I'm saying, that the fixed percentage, right? They don't have to actually be 80%, but there has to be a limit. That's my k. That's the limit of what the percentage could be. Okay, so the distance after you've done your function between those 2 points. So this here is my distance between f of x and f of y, and this is my distance between x and y. The distance after is less than or equal to this k times the distance before, and there is a k that you can find that it'll definitely be no more than 80% of the distance after. If all of those things happen, then there is a unique fixed point. And what do we mean by a fixed point? That means that is one point x with f of x equals x. So where the before is the same as the after. The after is the same as the before. So in terms of, I'll leave that there for a second. In terms of the picture I was drawing, if they all get closer together, it seems reasonable that if you do that, if you think about doing it multiple times, they'll get closer together again, closer together again, closer together again. They'll all get closer to something. That something is this point x. Okay? And so we're saying that somewhere in there, if they all get closer together, there must be one point that doesn't move at all. That's what this says.
Can you really prove that from that way?
Yes. It's right here, right?
Yeah, I get it, but I don't really get how one point can never move, because inside the set is limitless. So you can always move a point.
But if you move all the points in such a way that they get closer together, it is impossible to do that without leaving one point in the same spot. That's what this says. Magic, really.
Well, I'm just thinking of like a straight line. You've got 2 points, and then the rest of the points in the set either side of it. They can continue to get closer and closer without staying in one spot.
No, but we're not saying that the points, we're not saying those points are in the same spot. If those points get closer together, and these points get closer together, and those points get closer together, possibly none of those points I picked, there is some other point that doesn't move at all. Because the 2 points that you're talking about, this is x, this is y, this is f of x, this is f of y. This is f of x and f of y.
Yeah.
Okay. The f of x and the f of y are not the original. It's not like we're saying that, you know, x and y and f of x and f of y. It's not like those 2 points get closer together. It's the points after. So if you think about it, these 2 points get closer. So imagine you get a whole line's worth, right? And all of those points get closer together to each other. So the whole line as a block shrinks.
Yeah.
The whole line as a block shrinks. The whole line as a block shrinks. The point somewhere in the middle will have to stay in the same spot in order to maintain that shrinkage.
But I thought all the points had to.
So back here when I did my squares,
The distance between the points has to move.
the distance has to shrink, but the points don't.
Yeah, I get that.
But if the distance does shrink between points, so I'm going to see if I can draw a picture of it.
The point that they would merge, that's the limit.
That would be a limit. So if you picked one point and you did the function over and over and over and over and over, it would end up at the same spot as every other point would. I'm just going to draw this picture again. I'm going to draw them. Here we go. All right. This distance will get smaller after. Right? This distance will get smaller after, and so on. But what we're saying is that there is a point, maybe it's this point, for example, such that, this distance here got smaller, this distance here got smaller, this distance here got smaller, but the point itself didn't move. Everything else moved closer to it. Instead of that point moving in order to make the distances smaller, it stayed in the same spot. Everything came to it. There's exactly one point.
I mean, I get, like, sorry to
No, that's okay.
I get how that works. Like, it can happen like that, but can't it also be true that it doesn't happen?
No. The theorem, being a theorem, is true. It's surprising, but it's always true as long as all three of these things are true. So as long as it's definitely a contraction, and as long as it's your set is complete, so all the sequences converge. If the points in the sequence, if the sequence ends up being inside a little zone, it'll have to converge. Then it will have to be a contraction. So the only time it wouldn't happen was if it was possible for your sequences to not converge. Yeah.
Are you going to teach us how to prove that?
Sure. Let's do the proof.
Because, like, what is enough? What constitutes enough?
Yeah. So I was going to do proofs, but I ended up just doing all this. Okay, so I ended up just going through the concepts, but it seems that the thing that I really want to do, which will show you how to prove, I actually showed you how to draw, which is probably just as useful, at least for understanding. But for the exam, proving is good. So let's actually try and understand how to do the proof. And we're not going to copy necessarily. I'm going to attempt to not look at your lecturer's proof and try and. I might need to though. Okay, so the information that we have is this information here. That's where we have to start, okay? We have to start with that, do some words, possibly some calculations, and end up with this, f of x equals x. We're going to have to figure out, we can't just say f of x equals x along the way without telling my reader what x is, so I'm going to have to somehow point out that there is something that will, that there is an x at all, and then I'm going to have to show that it's the only x. Okay, so wrapped up in this is saying a unique point. Let's say there is a point. It's not 0, but it's also not 2 or 3 or 4 or 5. Right? So I need to show that there is a point that's fixed and that it's the only one. Okay. Now the fact that we have the statement that it's complete is hinting to me that we should probably use sequences, because completeness is about being sequences. Complete also possibly is about closed sets, so we might be able to do a closed set sort of thing. I'm just trying to think in my head of all the things that are connected to these ideas in the hope that they might help. So that's how I try and do proofs. All right? Cool. I'm going to cheat a bit. Just a minute. Okay. Right, so maybe instead of trying to, I can't think of how to show that the point exists at all, but I can possibly imagine showing that if there was a point that was fixed, it could be the only one. So maybe we should start there, and then I'll deal with trying to show that it exists at all later. Okay? So, well, we'll start. Start by supposing there is a point x such that f of x equals x, and we'll show that it exists later. Okay? There is at least one. Okay? There could be more than one.
Is that by contradiction?
No. So, yeah, I might do it by contradiction. Let's just suppose that there are two.
Now it's
There are 2 points, x and y, such that f of x equals x and f of y equals y. Because if that's false, then you'd have to either have none or one. Right? Because if there were 3, then there would be 2. So, yeah, we're going to start there. Okay. Right. So what else do we know about this thing? We know that the distance of f of x, okay, so we do know about the distances between f of x and f of y because we were told that, right? That's less than or equal to k times the distance between x and y, because that's always true, right? Okay. But f of x is the same as f of y, right? Like, so f of x is the same as x, because here, it's fixed. So this is from the statement that we had originally, df of x, xy is less than or equal to k dxy. That's from what we started with. But now let's look at this. F of x was equal to x. We just said that. And so this is equal to x. So we get, therefore, d of x. F of y is equal to y. Cool. Just a cotton picking minute. I could subtract d. Yeah, if d of xy wasn't 0,
And so because that's not true.
d of xy would have to be 0. So the only way that this could possibly work is if dxy was 0. But there's multiple ways.
They're the same point.
So they're the same point.
Yeah.
Well, just let me do some more. K is less than 1. So this would be strictly less than dxy if it wasn't 0, and that would be impossible. But I'm going to do it this way. And that's not possible because k is less than 1, which makes this positive, and this is positive, right? The only way that this could possibly be less than or equal to 0 would be if it was 0. That's how I would argue it, but you could argue it in any number of different ways. So 1 minus k is positive because k is less than 1, and dxy, so 1 minus k is strictly greater than 0, dxy is greater than or equal to 0, and so this is only possible, so therefore 1 minus k times dxy has to be greater than or equal to 0 as well, because this is positive and that's positive. So the only way that this can be less than or equal to 0 and greater than or equal to 0 is if it's equal to 0. Yes! 1 minus k dxy equals 0. Therefore dxy equals 0 because I can divide by that because it's not 0, and therefore x equals y. Yes! Because the distance between x and y is 0, so they must be the same point. It's only possible for the distance to be 0 if they're the same point. Whew. So there's actually, I thought there were 2, but they're the same as each other, so there's only 1. Okay? So in fact, at most 1 point x with f of x equals x. There might not be any, but there can't be 2. It's not technically a contradiction. In fact, it's not one word, by the way. I just didn't write a space. What you thinking?
Just what's the step you want greater than or equal to 0 and then just say it equals 0?
Because it's less than or equal to 0 and it's greater than or equal to 0, so it has to be equal to 0. Right? There are other ways of saying it. You could have said if dxy wasn't 0, you could divide by it, and then you get 1 minus k is less than or equal to 0, which is not true, and therefore dxy has to be 0. That would be another way of saying it. So, yeah, this is the one I happen to think of today. Now, in general, I'm a put everything on one side and put the 0 there kind of person. And it does help because I was aiming to talk about the number 0, so introducing a 0 somehow was a good plan. Okay, and now I have to show that in fact there is one. There is a point at all that is fixed. I have to use sequences, right? So far in my proof, I haven't used sequences. I've only used... So let's have a look. The function is a function. We've already used the fact that it's a function. We've used this fact about the number k already, at least once. We haven't used the fact that it's complete, and complete is all about sequences, so I'm going to have to construct a sequence. The only way I'm going to be able to prove this is constructing a sequence, because otherwise I'm not going to use that fact. So I'm going to have to construct a sequence, and now what does complete mean? Complete means that a Cauchy sequence must converge. Cool, so what I need to do is construct a Cauchy sequence. And then if I make a Cauchy sequence, then I can say, hey, the Cauchy sequence converges to a point that's actually inside my set, and that would be my point x. All right? Because that means that I'm able to say that x exists without saying what it is, because that's how Cauchy things work. Right? Because remember that Cauchy, the definition of it didn't involve the limit, but we knew the limit had to be there if it was complete. So I have to have some sort of fact that allows me to define that x is there without saying what x is. Okay? Okay, because otherwise my theorem would have told me what x was. It would have said, and in fact, x is this, but it didn't. Okay, so I'm going to have to make a Cauchy sequence. Okay, so a sequence is like a path, you know, it jumps from one point to another, and they all get closer together. I need to think of a way of constructing that path. Well, I have a way of jumping from one point to another already. That's what f does. It takes a point and moves it to a new spot. And then if I did f again, I can move to a new spot. So I should just do f repeatedly, and that can be my sequence. Excellent. All right. So let like x naught be any point in x, and then let xn be equal to like f of x naught. Oh, crap. N times. Okay, that looks like a good plan. I'm sure there's a better way of writing that, but it'll do. Okay. So what I've done just in my head, and this picture is not part of the proof, so I'll draw it in a different colour because you put it on your scribble paper or something. I've got my set x, and I'm going to move there when I do f, and then it's going to move there, it's going to move there, it's going to do there. So my before and after picture, I'm using my before and my after as the same picture. Okay? And then that sequence, we want to show it's Cauchy because then it'll converge. Yep? Okay. All right. So to do Cauchy, I'm going to need to do like dxn and dxm somehow. And that's d of f of x n minus 1 because xn I got by doing f on the previous point. And this is less than or equal to dk times dx according to my rule for contraction. Okay. That's not helpful, is it? Damn. See, I want to show that this is less than something. I want to show that if I pick my n and my m big enough, that I'll be able to make this distance less than epsilon if I pick an epsilon, because that's how Cauchy works. So I really back here I should say something like let epsilon be greater than 0, so that I can get to my less than epsilon eventually, because that's how Cauchy works. And then okay, so this is not going to go anywhere, right? I don't like it. But I could technically try and, if I did this long enough, I'd be able to get down to like d of like something and x0. Because if I did this again, because that's f of something, and then eventually one of them would get to x0, and it'd be the distance between something and x0. Nah. I know, I have an idea. What if I put the xn's and the xm's back by doing the triangle in it, by doing like a splitting it? Yeah. It needs to be less than something, right? Okay. So this is less than or equal to k times like that, because then I've got my xn back. Yes. Yeah, I'm looking at what he's doing. I've gone down a different road, so I'm just looking at what he's done. Oh, I see. Clever. So, he's saying x. Yes. So this one I can deal with. I can deal with that bit. So I'm not going to do this at all. I'm going to deal with that in a minute. Okay, so I'm looking at this. When I saw this one, I was going, just a second. This is f of that, and then I can do the k, right? I can remove the f's and put the k out the front, because that's how this works. And then I can do it again, because each one will be f of the one before. So if I keep pulling out f's, that'll allow me to put a k in. And so what I really need to do is I need to arrange for this first to do that. Like that. But then that's the triangle inequality. And then the triangle inequality, I'll leave this one as it was. And I'll split this one. So this is... so what I've done is I had the distance between xn and xm. And then I split that up into the distance between xn minus 1 and xn minus 1 and xm minus 1 and xm and xm minus 1. And because this is positive, this is less than or equal to this.
Have you got that written down right? Sorry, this question should be.
Sorry?
Xn minus 1. Oh, right, you just want to remember.
Yeah, sorry, I've just swapped the order because I was thinking of a picture in my head. So in my head, this one is xm, xn minus 1, and xm minus 1. That. All right, and this number here is positive. So this, oh no, that doesn't work. Crap. I'll just leave that for a second. Just leave it. Oh, yeah. Okay, doing really well. Watch closely. Okay. So we have that d. Oh, crap. The world turns to shit. So this is d of f of xn minus 1 and f of xm minus 1. Oh, I see. He's doing it backwards. That would have made so much more sense. damn. You can see why it took them until 1922 to prove this, based on metric spaces existing for about 100 years before that. So this would be, I can convert this into that because this is f of that and this is f of that. So if I pull the f out, I'll get the k. So I really should have probably just done a general one involving f's to begin with, like he did. But I was just trying to show you how you would come up with a proof, and it usually has several false starts. This is not the sort of proof that you'll do in your exam unless he says reproduce that proof. So, one more try. Sorry? Cool. So now we've got a really good reason as to why he's done the proof the way he has. I've got it now. Really good reason as to why he's done the proof the way he has. Okay, so the way he's done the proof the way he has, he's done d of xy. So he's done that triangle inequality first. And then that triangle inequality. And then he said, haha, using the rule we can do this. And that's got us to here. Okay, so we introduced the f's using the triangle. We made the f of x's and f of y's appear using the triangle inequality, and then we can make the f's disappear using our rule about k that we were told at the beginning. And then what we can do is if we put this over here, we'll have 1 minus k lots of dxy. So there's a really good reason why he did it this way. It was because when we tried to do it thinking about our original things, we kept having to fix it and going, oh, actually, that's not quite what I wanted. I wanted to do this. That didn't work. I need to do this. It would be much better if I started with m plus 1. And just a second. Let me just stop thinking about my actual situation and make it more general and try and do it with just random points. Just general points x and y instead of xn and xm. And see how I can get, if I can get something that means that I don't have to worry about all these m's and n's all over the place, and see what I can get. So I'm up to here. I get that. Divide both sides by 1 minus k. And there I am. So many brackets. Okay, this is good, because this is going to allow me to show that the distance between some points is less than or equal to something, which is a great start, because my aim is to eventually get less than epsilon. So for any point x, y, in x, I can say this. And then, okay. And so then let's look at our sequence itself. So the distance between xm and xn. Just a second. I'm just trying to think about it. Yep, all good. Okay. So this is, according to this rule here, this will be the distance between this number yeah. Crap. I give up. I like this. I'm just going to do it using that straight up. xm and f of xm plus dxn and f of xm over 1 minus k. I've got it. I should have just used it exactly as it said. Yeah, much better. I should have just used it exactly as it said. Okay, right. So I said that for any xy, this is true. So therefore this is true, because I just sub xm and xn into that. And then this is equal to, so this is equal to this, not that this is equal to this, because it's less than. This is equal to d of f of xm minus 1, f of xm minus 1, plus d of f of xn minus 1, f of xm minus 1 over 1 minus k. And I can pull a k out of both of them. If I pull a k out of this, because they will be less than or equal to n minus 1. Not a k. If I pull the f out, it'll give me a k. Okay, so I've done that step. If I continue the same process over and over and over, this can be f of xm minus 2 and f of xm minus 2, and then I can pull the f out and get another k. And then this can be f of xn minus 2 and f of xn minus 2, and I can pull the f out and get another k. And I can just keep doing that over and over and over and over and over until eventually that one will become this. And this one will become this. Awesome. I'm sure there's a better way of writing this. And so now the dx0 fx0 is in both of these, so I can pull it out. Okay, both of them have a dx0. I can pull it out of the top of the fraction and then pull it out of the whole fraction. Right. So, since k is less than 1, when I do powers of it, it will get smaller. Okay? So k to the n decreases as n increases, since k is less than 1. And so therefore in fact, it goes to 0, right? Therefore, this value can be made to be then epsilon by choosing large enough m and n. Yep, and it's okay to write it in words. This value can be made to be smaller than epsilon by choosing large enough m and n, and so therefore the sequence is Cauchy. And therefore, because it's complete, therefore the sequence converges since x is complete. And therefore, so if we call this limit x, we call the limit x, and we know that x is in x because it's complete, then f of x must be x. Because sequences, functions preserve limits of sequences. And he hasn't proven that part, he's just said therefore. But it is true. If you do f on a sequence, you'll do f on the limit too. So call the limit x in x, then the sequence f of xn converges to f of x, and therefore f of x must be equal to x, because the sequence of xn converges to x. Okay. I can think of a better way of writing that. I would have done this bit here with the dm minus 1 fm minus 1 as a separate part of working as well, because that would have made the working make more sense. So what if you say okay, just a second, I need to know how far apart any 2 points of the sequence are. But if I just pick a point, 2 points that are 1 apart, and find out how far apart they are, and then use that information to figure out how far apart any 2 points are. That's a contraction mapping theorem. So the Weierstrass theorem says, okay, right. So there's just only one more definition, by the way, which for completeness' sake I should put in here. A set is compact when any open cover of it has a finite subcover, where open cover means a set of open sets that covers the set. So what it means is this. Here's my set S. I imagine that I have some sequence of open sets that together cover the whole set. And it may be that I need a list of them that is infinitely long, okay, in order to do it. So it may be, so that's an open cover. U1 and U2 and U3, those sets cover the set. Open cover. It may be that you need infinitely many to do it, so you've got one here and 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 one here, and they get closer and closer together, right? You have to cover the bit in the middle too, so if I made them bigger. The point is that this one's got an infinite list that covers the whole set. Dot, dot, dot. The point is that it's possible among that infinite list to just choose finitely many and it will still cover, no matter what the infinite list is. Okay, that's what meaning any open cover has a finite subcover. So U1 up to UN, U2, 3, so U2, U3, blah, 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 is an open cover but can choose like U1 and U7 and U15 and, you know, doesn't have to be that, but you can just choose a list of them, which is still covers. Okay? And no matter which ones you pick, you can always choose a finite list. That's called compact. And that's great. It turns out that that's much easier than that. That while there are many crazy compact sets, there are some less crazy ones because they just have to be bounded and closed.
So could you just explain the open cover?
So an open cover is any set of open sets that covers your set.
Yeah.
But it doesn't have to have finitely many. It could have infinitely many. You could have to go U1, U2, U3, U4, U5, U6, U7 up to U infinity to cover the whole set. So the classic example is this one. I've got a piece of the line segment, and I can choose this set, and just a second. Sorry, just trying to think of this set. There's 0, there's 1. And I'm going to go this set, and this set, and this set, and this set, like just as lines on the interval, and this set, and I'll go half as far as I did before, just like when I did my sequences of a half and whatever. And if I keep doing that, I'm going to need all infinitely many of them to cover the whole set. But I can't remove any one. I'm going to need all infinitely many to cover the whole set, so this one's not compact.
Couldn't you just say that one cover can completely cover a set?
Sorry?
Find one and then you can just take out all the ones before.
But the point is, the point of compact is that if someone gives you an infinite set list, you have to always be able to choose a finite one that will work from within the ones that they just gave you. So you're right. I could just go, well, it's an open set. Duh, I'll just choose one. But a compact set says that no matter if someone gives you a list of sets that covers it, you have to be able to, within the ones, just the ones they gave to you, choose a finite list of them that works. And I can't do it with this one because it's not compact. So the infinite list one is only an issue really when it's not compact. Because if it is compact, you can cover it with a finite list. So, okay. So basically there's this theorem that says closed and bounded implies compact. But I have a feeling that there are some crazy compact sets that aren't closed and bounded. It's just that all the closed and bounded ones are. I can't think of any at the moment. So this is an open set, so it's likely not to be closed and likely not to be compact because it's not closed and it's not closed. Yeah. And I believe that an open set isn't compact. For that same reason, you can choose infinitely many, that you always need the little bit extra one to cover the edge. Okay, and then there's this final theorem, which is Weierstrass's theorem, which says S is compact and F sends S to the real numbers, then F attains its maximum and minimum inside S. So no matter, sure, you know, some functions have a maximum and a minimum, but because it might be an open set, the maximum might be just on the outside of the set. And so that's what they mean by attaining it inside S. Okay, so like if I just had an example S is from the interval from 0 to 1 on the number line, and f of x is like x squared, it's any old function at all, I'll draw it as a graph this time instead of my normal thing. Or maybe not. So I'm not using 0 or 1. No, I'll do it as a graph, just a second. It looks like that, right? But because I'm not using 0, I can't actually get to 0. The minimum is 0, but 0 is not in my set. Okay? So that's what the graph looks like. It should be a parabola, but I'm only using this bit. It does have a maximum. The maximum is 1, right? And it occurs when x is 1. But x is 1 isn't inside my set, because my set doesn't include 1 or 0. So because this isn't a compact set, sure, this function has a maximum, but the maximum doesn't occur inside my set. It occurs just on the edge. But if my set was closed, the maximum would happen, because it includes the edge now, which is where the maximum happened. Yep. Right. I think that's quite enough today. I'm sure that the Maths Learning Centre people will want me back for the exams that are tomorrow. Look, Maths Learning Centre is open next week. I know there are some other exams. Do you have exams? Is this the first exam? Yeah. Maths Learning Centre is open all next week. If come and talk to me, come in a group, sit at the same table. We can talk about doing proofs, and if there's enough of you all at once, I might just commandeer a tute room somewhere and do this, because I can take Flenchy and do an impromptu one if you're there, and we can talk about the proofs then. But there you go. That's my pictures of metric sets.